In this video, we continue our treatment of the linear unobserved effects model for panel data, this time around discussing the first difference method of estimation. So let's discuss first difference methods, starting with the first difference transformation, which will lead us into the first difference estimator. Recall that the linear unobserved effects panel data model treats the outcome as linear in regressors from the same time period up to the sum of two unobservables, one being what will denote the individual effect or unobserved effect, CI, which is time invariant, and one which is allowed to be time varying, which we'll denote by UIT. If we lack this equation, again, this equation is presumed to hold for capital T periods of time. If we lack it one period of time and subtract the resulting equation from our original equation, we arrive at an expression for the differences in outcomes in two adjacent periods, stating that it is linear in the differences in regressors up to an unobservable term, which is composed by the differences in the original unobservable terms. Note here that in computing the differences, since the individual effect, or CI, is presumed time invariant, it is the same across all time periods, such that by conducting this differencing, we cancel out the individual effect. Again, we've successfully eliminated the time constant CI from our equation, this time around arriving at an equation or estimating equation, which is linear in the parameters, but it's expressed in terms of variables which are stated in first differences. So here our delta notation, for example, delta YIT, is short for yi in period t minus yi in the preceding period. All right, note that when we compute differences, since we have nothing to do in period 0, since we don't have data for that period, we can only compute differences in periods 2, 3, and all the way up to capital T, whatever that may be. That is, we lose one period of time. Now, also, I want to stress that, again, this equation in first differences is just an estimating equation. When it comes to the interpretation of the parameters beta, we should go back to our original, what we may think of as the original structural equation. So what is the first difference estimator, or FD estimator? It is simply pooled ordinary least squares using the difference data, or first difference data. Here I've written out the first difference estimator, stressing that we're pooling all the data, pooling all the pairs of I and T that are available for estimation. Note here that the inner sum runs from t equals 2 to capital T, since we've lost that one period of time. Now the first expression is neat in stressing that we're just using pooled OLS, but we can also rewrite this formula in a way that is more concise and more amenable to computation. So let capital boldface X denote the matrix that arises from stacking the XITs, or rather the first differences in the regressors, for a given individual chronologically over time, and then over all individuals. Since we've lost one period of time, that yields a matrix of dimension n times t minus 1 by k. We can do the same for the outcomes. The same type of stacking yields a vector which is n times t minus 1 by 1. I want to stress here that there is one potential pitfall that arises from first differencing. That is, when you're manually conducting the differences, you should be careful not to suddenly create ghost observations. And by ghost observations, I mean you should remove the rows of data that arises from comparing data for one individual in the first period with data for another individual in the last period, which will pop up when you do the differencing in a manual manner if you're not careful. Having defined the first difference estimator, we can proceed to derive various properties of this estimator. The assumptions that we'll work with will simultaneously yield identification of the model. So the first assumption that we'll invoke is the strict exogeneity assumption, conditional on the individual effect, from our earlier video on the fixed effect estimator. So this assumption, what we'll denote assumption FD1 for the first difference assumption, is exactly FE1, the first fixed effects assumption. It states that the conditional mean of the UIT in any period, conditioning on the XITs from all periods as well as the individual effect, it's equal to 0. Now, from this assumption of strict exogeneity of the regressors, one may show that the usual type of OLS assumption, or the analogous assumption, the assumption that is analogous to our OLS1 type of assumption, holds for the first difference variables. In fact, one may show that we can get by with a weaker type of assumption, stating that the conditional mean of UIT in any period, when conditioning on regressors in the same period as well as the preceding and following periods, should be equal to 0. This follows from just expanding on the product of the first differences and seeing that we never encounter anything but products that involve variables within one period of time. However, making this type of assumption, where we are willing to assume this within one period type of exogeneity, I would be hard-pressed to come up with an example where such an assumption is appropriate, while the assumption of strict exogeneity is not. Hence, we will proceed with our already stated assumption of strict exogeneity. Of course, an exogeneity assumption is not enough in order to obtain neither identification nor consistency of the estimator. So we'll invoke also a rank condition. For this purpose, we will stack the differenced regressors and differenced outcomes over T for a given individual in order to write the first difference estimator in a manner which looks a lot like the OLS estimator in the cross-sectional case. Now here I want to stress that this vector of outcomes, this delta yi, is a t-1 vector of delta its. Similarly, this delta boldface xi is t-1 by k. However, from inspection of this formula and from arguments that run completely in parallel to the cross-sectional case, we may deduce that the relevant rank condition for first differencing is to assume that the expected product of the first differenced regressors, as I'm writing here in braces, which is a k by k matrix, that this K by K matrix should have full rank, which means that it should have rank equal to K. Now we could expand on the product of these first difference regressors to see that it constitutes a sum of the outer product of period-specific first difference regressors. And since we can pull the expectation inside the sum, we see that the relevant rank condition can also be stated as the sum of the expected outer product of the period-specific regressors should be equal to K. Now, since we're computing differences, this condition is bound to fail whenever xit contains one or more time constant variables. For example, xit cannot contain an intercept, nor can it contain variables such as gender or ethnic origin, that is, ethnicity. All right, having established well, one may show that under these two assumptions, that is the strict exogeneity assumption and our newly introduced rank condition, one may show that the coefficients of the model are identified and also that the first difference estimator is consistent. The arguments run in parallel to our already discussed case of the fixed effects estimator, which in turn builds on our knowledge from the cross-sectional case. But I encourage you to go through these arguments step by step at your own pace in order to verify that you've understood all the arguments. Let's move on to talking about efficiency. Now, one may show that in parallel to our analysis of the fixed effects estimator, in order to establish efficiency, it suffices that the following assumption hold. So, in order to state this assumption, let EIT note the first difference UIT for each period 2 all the way through capital T. Then our third first difference assumption states that the matrix resulting from the outer product of the EIs, which are the EITs stacked over time, this matrix in expectation conditioning on the regressors in all time periods as well as the individual effect, this matrix should reduce to a scalar matrix. That is, we can, under this third assumption, we can write this matrix as the identity matrix up to a factor of proportionality, which we'll denote here by sigma square E. Now note here that this matrix, since we've lost one period of time, this matrix is t minus 1 by t minus 1, such that the identity here is t minus 1 dimensional. Now this assumption implies that the EIs are homoscedastic as well as serially uncorrelated. Homoscedastic in the sense of having the same variance across time within a given individual. And the serial or uncorrelatedness comes from the fact that the identity matrix is 0 off the diagonal. This means that the differences in the UITs are homoscedastic as well as serially uncorrelated. And in fact, this assumption, since we're conditioning on all of the XITs as well as the individual effect, this homoscedasticity and serial uncorrelatedness must hold in a conditional sense as well. Now one may show that, just from definition of the EITs, one may show that under the third first difference assumption, we can write UIT as the lag of UIT plus a term which is homoscedastic and serially uncorrelated. That means that UIT follows what's known as a random walk. And random walks are known to exhibit a high degree of serial dependence, that is, dependence over time. Conversely, if we start out with the UITs being serially uncorrelated, for example, if we were willing to believe in the third fixed effects assumption, then the process of first differencing induces serial correlation. That is, it yields differences in the UITs which are serially correlated. As a result, the third first difference assumption would fail. In fact, the third first difference assumption and the third fixed effects assumption are mutually exclusive. One rules out the other. And our discussion here of a random walk versus uncorrelatedness show that they represent opposite extremes. Now, going back to our discussion of efficiency, one may show that under the first difference assumptions 1 through 3, the first difference estimator is asymptotically normal and also asymptotically efficient. Again, these arguments run in parallel to the fixed effect estimator, which in turn runs in parallel to our discussion of the cross-sectional case with the OLS estimator, but I highly encourage you to go through these arguments step by step, verifying that you've understood all of the elements going into them. We end this talk by discussing methods for consistently estimating the asymptotic variance, which would allow us to do inference, say using a Walt type of test. Now one may show that, as I already mentioned, under these three first difference assumptions, the difference between the FD estimator and the parameters that we're trying to estimate, when scaled by root n, converges in distribution to a normal distribution. And one may show that the asymptotic variance is just sigma square E times the inverse of the expected product of the first difference regressors. Hence, our estimator of the asymptotic variance of the first difference estimator, which here is just this guy divided by n, can be obtained by replacing the expectation by an average and inserting a consistent estimator of sigma square E. That's exactly what we've highlighted here in the displayed equation. Now, a consistent estimator of sigma squared E is obtained from the usual calculation, where we gather the sum of squared residuals from the first difference estimation, and then we average them. Here again, we've included this degrees of freedom correction by subtracting k corresponding to the number of parameters in our model. Note here that these formulas correspond exactly to what would be spit out as a standard OLS type of variance estimator, say using a canned routine in Stata. Now the reason for the standard OLS variance estimator to hold in this case is that the n times t minus 1 is in our case the effective sample size. And we are not implicitly doing an estimation of n individual specific intercepts. The reason for the n times t minus 1 to be the effective sample size is that we've differenced once, thus lost one period of data. Now, of course, the preceding discussion here is only relevant if we're willing to impose the third first difference assumption, which may or may not be what we want to do in an empirical setting. Of course, one may also establish asymptotic normality without the third first difference assumption, and one may show that under the first two first difference assumptions, that is strict exogeneity as well as a rank condition, you can show that the difference between the first difference estimator and the parameters that we're estimating, when scaled by root n, is asymptotically normal with a sandwich type of variance. So think of this as our v. Now the breadth of this sandwich is as before, where it mimics what we've already seen for the fixed effects estimator, as well as in the cross section. But now the meat here is complicated by the fact that we have t-1 residuals, right? So our residuals here, or rather here we're dealing with the errors. The errors here are t-1 vectors, such that we have to respect the various dimensions in order for this matrix to be composed by conformable objects. This is similar to the fixed effects case. So how would we construct a robust variance estimator? Well, we would simply replace A and B by consistent estimators and divide by n. And that's what we've done in the last display down here, where these boldface EI hats represent the vector of first difference residuals, one for each of the t-1 periods of data that is available. One may show that this variance estimator is consistent under first difference assumptions 1 and 2, that is strict exogeneity and a rank condition, and it is robust in the sense of not relying on any sort of homoscedasticity or serial uncorrelatedness. Having discussed both the fixed effects as well as the first difference estimators, you may wonder at this point, what sort of estimator should I use? Now, since both of the estimators rely on our assumption of strict exogeneity, then up to rank conditions, which we believe to hold quite generally, the choice between fixed effects and first differences is really about efficiency. However, one may show that in the special case, where we just have 2 time periods available, so capital T is 2, then first differencing as well as going within or calculating the fixed effect estimator are algebraically equivalent. This follows from the fact that the within transformed variables and first difference variables only differ by a proportionality factor, which is what I'm stressing in this display. And I encourage you to go through, for example, one may show that the fixed effects estimator, the within transformed outcome for period 2 for this particular individual, given just 2 time periods available, it can be equivalently expressed as 1/2 times the first difference outcome in period 2. Similar expressions hold for the regressors as well as the outcome in the other period, perhaps with an opposite sign. I encourage you to use these 4 expressions and insert them into the formula for the fixed effect estimator in order to see that it actually reduces to the same formula or to the formula for the first difference estimator. Now, the previous discussion here was all done under our assumption of strict exogeneity. If this assumption fails, then we have to do something else. Now, one can show, or it turns out that the idea of fixed effects or going within is almost impossible to salvage when strict exogeneity fails. However, one may show that the idea of first differencing is slightly more robust and is somewhat salvageable, at least under some assumptions. That is, we can get by with less. And this is really where first differencing, or the idea of first differencing, truly shines. But more on that in a later lecture.